All right, guys, we're gonna finish. It's not finished, but continue to work on section 3.6. Obviously, not last week, but the week before, the Thursday before last week, we had kind of started 3.6, and we did a quick introduction to rational functions in regards to kind of using transformations to deal with them. For instance, we started with, to give you a quick refresher here, started with something that looked like 1 over x, and kind of talked about how if we take 1 over x and we start dividing with x values that are very, very large, 1 divided by a very, very large number is close to 0, right? Okay. Take $1, break it up amongst 1 million people. Everybody's going to get something, but it's going to be very, very, very small, right? Okay. Now, it doesn't really matter. I say 1, but it doesn't really matter what that number up top is. I take that number up top and be 1,000. Take $1,000 and divide it by 1 million people. Okay. Zoom out here. Disappeared on the left too. Like a 1,000 divided by x. Okay. Even though that's a larger number than 1, right? What happens as x gets really, really big? What are we starting to do?
It gets closer and closer.
Yeah, it gets closer to 0 again, right? You take a number and divide it by something that gets extremely large, okay, in comparison to the number that you're dividing, you're going to get 0, okay? And the same thing happens is that number is very, very, very small. I guess a similar thing happens, okay? I take again 1 over x, and, come on, there you go. 1 over x, and I take x to be a very, very, very small number, okay? So take 1 and divide it by something very, 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 very small. That number should go to infinity. Does that make sense? 1 divided by 0.000001. Okay, relatively compared to 1. Another 1 is much bigger than 0.000001. And when I divide them, I'll get a very, very, very large number. Okay. So we talked about that concept. Okay, and that's something that maybe if you struggle with right now, that's confusing you, go back and watch that video from 2 weeks ago. Okay, it's posted online right now. But that concept is going to be kind of the foundation for everything that we do in this section. Okay. Now there's going to be a lot of algebra that we have to do in this section. Okay. I think the last class we talked about there's potentially like 12 steps, 12 different things we have to look at to develop a graph. Okay. By hand. Now, obviously you're saying, well, why do 12 things? Why not just use our calculator because it's going to give us the graph a lot easier? Yes, you're right, and we will do that. But there are still times that your calculator is not going to do everything that you need it to do. Okay? So we need to be able to do some of this stuff by hand. So we got f of x equals 1 over x. Let's say that I take, instead of 1 over x, let's go 1 over x minus something. And let that be something be value we could change between, let's just go -1 to 5, or -5 to 5, that equals 1. Alright, so if we have that, I'm going to put in that red dotted line. I'm going to force that to be the value in which the denominator is not allowed to be. Okay? The denominator cannot be 0, right? In this case, 1 over x. Okay. So when I put in that red dotted line, what does that red dotted line? What do we call that? That's where the denominator cannot be equal to 0. It becomes an asymptote, vertical asymptote. Okay. A vertical asymptote is the visual that we have or that we need to remind ourselves that there is no y value that goes with, in this case, x being 0, Because that gives you 1 divided by 0. It gives you an indeterminate value. So the visual is put a vertical asymptote there and you remind yourself that you cannot cross that thing. Okay? Because we can't, and why can't we cross it? If you go back to Algebra 1, didn't we talk about whenever you cross something, that is when the two curves were equal to one another, right? Okay? Well, here, you cannot have the green curve equaling 0. Okay? Does that make sense? So, what happens then when I start changing that a value? Look what it does to the denominator, x minus 1. It now just shifted everything 1 unit to the right, correct? And that's what we should know with transformations. Subtract from x, and it moves it to the right. Okay? But it moves everything. It moves the asymptote as well. Okay? What is nice about that is if I take x minus 1 and set it equal to 0, take my denominator and set it equal to 0, it provides me the location of that asymptote. Okay? And that's something we've been doing. And if you remember back to chapter 1, we did a lot of domain stuff, right? A lot of questions about domains. Okay? And we had rational functions. Okay? Anytime we were dividing with domains, we always want to look at where the bottom was equal to 0, right? Well, this is just the application of it. This is one of the reasons why we were doing that. Okay? If it becomes x minus 2, you see that x minus 2 equals 0. Solve for x. X ends up being 2. And there's my red dotted line at x equals 2. And that's an asymptote for that function. Is that doable? Okay. Now what happens is that we can eventually have things like this, where I'm going to put in x equals b as a vertical line. Okay, and you see now the denominator, x minus 2 times x minus 1. If I set both those things equal to 0, do I get x equals 2 and x equals 1? And do you see that graphically represented then in your image with your asymptotes? Okay. And again, we can change those, we can move those around. Okay. You start to see it that the b factor, okay, the x plus 2.35 in this case, is going to move that asymptote. It's just trying to move that to a nice value there. And this one here moves the other one. Okay. But what happens is that in a homework assignment or on a test or a quiz, or when you're in calculus and you're trying to do something, you're trying to maybe integrate this function or differentiate this function or something like that, it's probably not going to be provided to you in that form. It's probably going to be provided to you as 1 over x squared minus x minus 2. It's going to be in expanded form. Does that make sense? Okay? But that expanded form, though it's useful in some aspects, this form is also useful. Okay, so it's going to be imperative that we know how to factor. Okay, and that's why we spent so much time early on in chapter 3 learning different techniques for factoring. Okay, because we might have a numerator that's a cubic and a denominator that's a quartic, and we want to factor that thing, both those things, to see where asymptotes exist. Does that kind of make sense? Okay. So, like I said, eventually it's going to look like this: 1 over x squared, let's say minus x minus 2, and you see that that red curve is exactly the same thing we had up here in green. So you're going to see it written as this way in a homework question, and you need to get it to this portion or this format so that you can find where these asymptotes actually exist. Okay. But that being said, doesn't necessarily have to be just 1 on top. It could actually be something a little bit more interesting on top. Maybe I say x plus 3 on top. And now you start to see maybe a little bit of a different relationship here. Okay, now my asymptote, okay, is no longer, I'm sorry, I was saying my vertical asymptote is still going to be 0. Okay, so the horizontal asymptote here is 0. But you see here in this one, kind of interesting feature that you don't always get with horizontal asymptotes, but we cross this one, don't we? Okay. And we'll talk about some nature and some, looking at this right away off the bat. I don't know that I cross it. Okay. But we'll do some algebra that kind of tells me that yes, indeed, you do cross it, and it'll tell me that it happens here. It looks like -3. Okay. So we're going to try to kind of develop the techniques and the step-by-step procedures that help us develop this picture. Is that all right, everybody? Okay. Something that is that as we do these things, okay, think about this one here. If I look at this function, okay, and I think about 1 over. These two things are the same, right? The green one and the red one are the same thing. If I think about 1 divided by x squared minus x minus 2, and I start choosing x values that are pretty big, and when I say pretty big, that's a relative statement. It could be 10, okay? 10 squared is 100, right? Minus 10 is 90, minus 2 is 88, right? What's 1 divided by 88 pretty close to? 0, right? Okay. If I come out here to an x value of 10, my y value is pretty small, right? Okay. If I look at x being something larger than that, you can start to see that I'm going to have 1 divided by something a lot bigger than 88. And then again, the idea is that I should be getting down close to 0. Does that make sense? So that was the idea that I'm going to take 1 and divide it by a very large number. Okay. 1 divided by a very large number should be close to 0. Okay. Take and divide by, let's let x be like 2.1. Okay, 2.1. If x is 2.1, okay, I have 2.1 minus 2 here, right? So 2.1 minus 2 would be 0.1, correct? Okay. And then I have 2.1 plus 1, so that's 3.1, right? Well, 0.1 times 3.1 gives me 0.31, right? Well, 1 divided by 0.31 gives me 3.2258. Okay? So when I'm at 2.1, I should be up at a y value of about 3.228. Sorry, 2258. So about right there, right? Now let's say that I take that 2.1 and I make it 2.001. Okay? Well, 2.001 minus 2 would give me 0.001. And then I'm going to multiply that by 3.001 because that's going to be 2.001 here for this x plus 1 will give me 3. Okay? Multiply that, gives me that number. Now take 1 and we'll divide it by that number there, 0.003. Hit enter, and it gives me 333, right? So you see that the closer I get to this asymptote, okay, on the right-hand side, this number starts to shoot up towards what? Infinity. Okay? And that's the nature, that's the exact same nature that we had when we had something like 1 over x. And I said, okay, choose a number that's very, very close to 0. Okay? You get 1 divided by 0.0000001. That's going to shoot up towards infinity, right? Okay? So the same behavior that we see in regards to those asymptotes for 1 over x is the same type of thing we're going to see in the asymptotes for 1 over x squared minus x minus 2. Okay? Asymptotal behavior is the same regardless of the functions you're dealing with. Okay? Now, because of our algebra, there's going to be some tricks that we can go through, some shortcuts, but I want to make sure we understand these shortcuts and why we can do them. Okay? So the PowerPoint kind of gets into, at first, determining what we can do for horizontal asymptotes and how we find our horizontal asymptotes. Okay? Hopefully the GeoGebra concept that I just showed you gives you an idea how you find your vertical asymptotes. your vertical asymptotes are always located at your domain issues, right? Okay, and domain issues are when we divide by 0 for these things. So I just set my denominator as equal to 0, and that will allow me to find my vertical asymptotes. Okay, and that might incorporate you having to do quite a bit of factoring. Okay, and then we go back to factoring. We now have pretty much every tool that we've ever needed to factor. Okay, that's what we spent chapter 3 in algebra 2 and algebra 1 on. I was learning these techniques to factor so we can address things like this. So now we want to talk about the horizontal asymptotes. Okay, and you got 3 scenarios that can exist for horizontal asymptotes. Okay, or to provide you information about having or not having horizontal asymptotes. Okay, it says in general, if your R of x, if your rational function, which is equal to 2 polynomials divided by one another, okay, and those 2 polynomials, P and Q, are of the same degree, okay, and in this case, they're saying both are n, okay, so we have something that looks like R of x maybe is equal to like 2x, let's do it real easy, 2x cubed divided by 3x cubed. If we have something like that, okay, would you agree that they're both of the leading degree n, where n in this case is 3? Okay. If the leading degrees are the same, okay, think about what happens in the long run as x gets really, really, really big. If x becomes 10, you have, what's 10 to the third? 1,000, okay? So what's 2 times 1,000? 2,000. What's 3 times 1,000? 3,000. What's 2,000 divided by 3,000? 2/3, right? Okay. What happens if x is 100? 100 times 100 times 100, right? Okay. Well, that's what, 6 zeros? So that's 1,000,000, right? Okay. You have 2 million divided by 3 million. What's that give you? 2/3. Okay. So as x gets really, 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 really big here, okay, it's getting amplified on the top the exact same way that it is getting amplified on the bottom. So why even deal with that? Why even worry about those? Cross those out, because they do reduce anyways, right? And you get R of x equals 2/3, or y equals 2/3. And that provides you where your horizontal asymptote is located. Okay? Does that make sense? So when you have leading degrees that are the same, okay? When they are the same, you simply just look at the leading coefficients. So let's kind of take a look at this. I've got, let's just go f of x is equal to a times x minus b divided by c times x minus d. All right, so hopefully you realize that that's not really interesting when I just changed the a value, right? Okay, I got x, and we'll talk about what x minus 1 over x minus 1, that reduces, right? Gives me 0 or 1 there. So I have -2 over 1 times 1 gives me the line y equals -2. But when I start changing the b values, the c values, that kind of stuff, we start to see the graph change a little bit. Let's kind of do this. Let's take a over here to be 3. So we get that graph. Okay. Let me put in my my vertical asymptote. Where's my vertical asymptote going to be here? X equals 3, right? Take the denominator, set it equal to 0. Okay. And I get a vertical asymptote at 3. Okay. So right there. Now, you notice that my horizontal asymptote, like in the past, my horizontal asymptote was the x-axis, right? Well, now you see that it's really not the x-axis. As I keep going further and further this direction, I'm not approaching 0, am I? No. And as I go in this direction, now I get closer and closer to 0, but there's going to be kind of a cutoff that I'll never get beyond. Okay, I'll never get low enough to actually get to 0. Okay, so how do we find that? Okay, well, because these two numerator and denominator, okay, this is 3x plus 3 on top, right, and 2x minus 6 on the bottom, because they're both to the first degree, they have the exact same leading degree, we can find our horizontal asymptote just by comparing the leading coefficients. And the leading coefficients here are 3 and 2, right? Okay, so our leading coefficients is 3 over 2, so we divide those, gives us y equals 3/2, and there is our horizontal asymptote. And that should kind of make sense graphically to us as we move further and further to the right, and we move further and further to the left. Is that doable? Okay. In your homework, you're probably not going to see it written that way. In your homework, you're going to see it written this way, where they say your function is equal to 3x plus 3 up top, and 2x minus 6 on the bottom. So I can give you that function right there. Okay, and in that format, it's maybe a little bit easier. See, yeah, they're both of the first degree. Don't even worry about the plus 3 and the minus 6, because when x becomes really, really big, when x is 1,000,000, if you add $3 to that, is that a big deal to a millionaire? No, so that plus 3 in the numerator is negligible when x is really, really big. Okay, if you have x to be 1,000,000, and you put it in the denominator, and you take 2 times 1,000,000, you get $2 million, right? You take $6 away from a person that has $2 million, do they really notice it? No. Okay. So you have basically 3 million up top and 2 million on the bottom, and that reduces to 3 over 2. Is that doable? Okay. So that's the idea of how we find horizontal asymptotes when your leading degrees are the same. So, for instance, if I take the graph will look drastically different here. If I take 3x squared up top, 2x squared on the bottom, and I do that, okay, let me hide that one. There's that graph right there, right? It's a new function, completely new graph, but because the leading degrees are the same, okay, the plus 3 and the minus 6 are negligible, okay? Even if the plus 3, let's say it was an x there and an x there. Now, I'm just going to change the graph. But look at that. Okay? 3x squared plus 3x, 2x squared minus 6x. Let's think about this. If x is 1,000,000 and you square it, you now have a 1 with 12 zeros behind it, right? You got quite a bit of money, correct? Okay? Now, if you have a 1 with 12 zeros behind it in your bank account, and somebody adds to it $3 million, is that nice? Yes. But is it very large in comparison to the 1 with 12 zeros behind it? Not even close. 1 with 9 zeros is $1 billion, right? Okay. You guys know how big a million is compared to $1 billion?
Kind of small.
Okay. I turned 33 last week, and I recently reached my 1 billionth second of life. I think like 32 in 6 months or something like that, you have to turn 1 billion seconds old. Okay. So it's quite a bit of, it's a very large number, right? A million is like several years, okay? But a billion seconds is a very, very large number compared to a million, okay? So if I have a billion squared, think about that, okay? And then I add 3 billion to it. It's not, that 3 billion that I'm adding to it is negligible. It doesn't really impact the total, okay? Same thing on the bottom. If I have a billion squared on the bottom, multiply it by 2, and then subtract 6 times a billion, that subtraction of 6 billion is not going to impact that bottom very much. Does that make sense, everybody? So even though it's not just a constant getting subtracted or a constant being added in this black function, I still have leading degrees of x squared and x squared. So that's what I want to look at. I want to look at their coefficients, and I see 3/2. And you see graphically, you know, is that dotted curve still approaching 3/2 in both directions? Okay? So that's how you deal with horizontal asymptotes when the numerator and denominator's degrees are the same. Okay? So then that maybe leads you to the question, well, what do I do if they're different? Well, there's one situation where it's really easy to determine what you do when they're different. Think about this. Would you agree that if we look at that black one, those leading degrees are different. The one up top is to the first power, and the one on the bottom is the second power. Would you agree with that? Okay. Which one is bigger? The one on the bottom, right? Okay. So if I take that one on the bottom, no markers? Huh? I can't reach my chalkboard. That's why there's nothing written on it.
Why would you put it up before you wrote on it?
It's crooked too.
Why
Why don't
would
we
you
just
put
take
it?
that one?
Just wanted to see if I could put them up.
What about that
If
one?
they'd stick.
Shoot.
All right, so we have 3x, 2x squared minus 6x. Okay? So this leading degree of 1 is smaller than that leading degree of 2, right? Now here's the algebra that allows us to get to the conclusion that we're going to make. Because what does our horizontal asymptote here look like? I'm going to try to get rid of that line, but okay. Look at the dotted curve. What is our horizontal asymptote? It's 0, right? It's the x-axis again. Okay? So how can we know that? Okay? How can we algebraically show that? Well, think about this. If I look at this function, and I have 3x up top. Now I'm going to take this bottom one. I'm going to factor out an x. So when I do that, it's going to give me x minus 6, right? Now what can you do with that x and that x? Those cancel, don't they? It leaves you just 3 over x minus 6, right? Does that make sense to everybody? Now think about this. In the long run, as x goes to 100, goes to 1,000, 10,000, a million, a billion, you have 3 divided by a very, very, very large number, don't you? And a number divided by a very, very, very large number is going to approach what? 0. Okay? So this quotient, as x goes to infinity, okay, that quotient becomes 0. And that's what we're thinking about. As x goes to infinity, what does that y value become? In this case, it becomes 0. Because of that idea of being able to factor out. If I had, let's just say, let's go 3x squared plus x over, I don't know, 5x to the 5th plus 4x cubed plus 2x plus 7. Something like that. Okay? Do the same type of thing. Okay? Up top, what can you factor out of the stuff up top? X. So we get x, and then I'm going to have 3x plus. Actually, let's do it this way. I know I can factor out x, but I'm going to factor out x squared. If I factor out x squared up top, okay, that's going to leave me with, what, 3 plus 1 over x, right? Does that make sense? I'm going to talk about why we're doing that in a moment, okay? I'm going to factor out an x squared on the bottom. Factor out an x squared on the bottom. Now, talk about why we're doing this in a minute. But that would give me then 5x cubed there, right? Plus 4x to the first there, okay? Plus 2 over x plus 7 over x squared, right? Okay? Now, the reason I've done this is I just looked at the numerator and said, what was the largest degree in the numerator? Let's factor that out. And then just factor the same thing out of the bottom. Because I wanted to see what cancels. And we see here that we at least get those things to cancel out, right? So being able to look at this should give me the same results as looking at this. Okay, does that make sense to everybody? Okay, at least in regards to x being very, very large. If x becomes very, very large, what does that number go to right there? 1 over x. What's that become? 0. When x goes to be a very, very large number, that becomes 0. What's this number become? 2 over x. 0, right? It just does it a little bit slower than 1 over x did, because the numerator is just a little bit bigger. 7 over x squared, that becomes 0 a lot faster because of that x squared, right? So really what this gives me is when x is really, really big, it gives me 3 over 5x cubed plus 4x, right? Now think about that thing. When x is really big, even when x is 10, 10 cubed was 1,000, right? Times 5 is 5,000, plus then 40. Well, 3 divided by 5,040, pretty small number, right? Now let x become 11 and 12 and 13 and then 100 and 1,000, okay? What's this number going to go to? 3 over a very, very large number, right? So it becomes 0, okay? No matter what you start with, no matter what these degrees are, that's why I kind of wanted to do this one, okay, in comparison to what we did here. As long as that degree there is smaller than the leading degree there, you will always be left with something like, after you do a little bit of factoring and canceling out, you're always going to be left with pretty much a constant up top, okay, divided by a very, very, very large number, okay? And a constant divided by a very, very, very large number is always a very, 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 very small number, right? Very close to 0, okay? So, what you'll see in the PowerPoint, they kind of, they break it down kind of to a generic concept, using generic terms or generic polynomial format. And this is the when I was in high school, it was just taught to me these things, okay? And I would forget these rules or I'd mess them up or something like that. I think I understood this stuff so much better when I looked at it using this algebraic concept and understood it algebraically here. Because then if I did forget one of these, I could still at least work in my problem and say, okay, now what happens? I know that a horizontal asymptote, we're interested in that in behavior, so x is getting really, really big. What algebra can I do that would lead me to the correct conclusion here? The correct one of these A, B, or C options that they're telling me, okay? It says if we have the rational function, okay, r of x is equal to a polynomial divided by a polynomial, all in that ugly notation that we've talked about in the past. I want to come down to number 2 here, and it simply says these are the 3 options that could occur, the 3 situations that could occur when you have 2 polynomials divided by one another. Your leading degrees, your numerator, okay? This PowerPoint shows n over m. I see a lot that use like a over b for your exponents. Okay, it doesn't really matter what your exponents are generically. But if the numerator's exponent n is smaller than your denominator's exponent m, so that's this situation here, right? That's our n. N is smaller than our m, right? Up here, our n was 1, our m is 2. 1 is less than 2. In this case, 2 is less than 5. If that's the case, every single time you get a horizontal asymptote at y equals 0. Okay? Every single time. And that's because this algebra can be done every single time. And you make the conclusion, okay, as x gets really big, I've got a small number divided by a huge number, and that gives me 0. Okay? So that's something to remember. That's a shortcut that we can use to find the components of our graph a lot easier. Okay? Part B is, well, what happens when they are the same? When the exponent, or the degree, I guess, of the numerator is identical to the leading degree of the denominator. Okay? So that was the idea that we saw in the previous example. We saw then that you simply find your horizontal asymptote by dividing your leading coefficients. Okay? So that was the case, like if I had, keep taking my markers and run away with them. If I had like 3x squared over 2x squared, well, the x squared is going to cancel out regardless of how big x is, right? X goes to 1,000,000, then 1,000,000 squared divided by 1,000,000 squared gives me 1, doesn't it? Okay? And then I had 3 on top and a 2 on the bottom, so I have something like this. So 3 times x squared over 2 times x squared. Well, if x is 1,000,000, I have 3 times 1,000,000 squared over 2 times 1,000,000 squared. Those go to 1, don't they? And all you're left with then is 3/2 times 1, which is now your y value. Okay, so you're reaching an asymptote of your leading coefficients. Okay. Now part C is when the numerator is bigger than the denominator. Okay. So now think about it this way. If just give you a quick example of this, r of x. Let's say we have I don't know, 3x squared over x, okay? If I go through and do the division there, do the cancellation, I get 3x, don't I? And what is your y value going to become as x goes to a very, very, very large number? X goes to 10, I get 30, right? X goes to 100, I get 300. X goes to 1,000, I get 3,000. X goes to 1,000,000, I get 3,000,000, right? As x goes to infinity without bound, what is y going to? Infinity as well, okay? So what that provides is that last option C, when your numerator is bigger than your denominator, when those degrees are different in that order, in that fashion, you get what we call an oblique asymptote, okay? You guys remember back to geometry, when I used the word, we talked about prisms, we talked about cylinders, and a lot of times we talk about right cylinders and right prisms, but there was a special type of cylinder or a special type of prism that we mentioned, and it looked something like this. Would be a right cylinder, right? Anybody remember what that one was called? It's kind of leaning to the side. Oblique, okay? You know what these muscles in your sides are? Your oblique muscles, right? Your abs on the side are obliques. So something leaning to the side is oblique. Well, when I lean to the side, I got a little slant to me, right? Got a little slope to me, right? Okay? So when you have an oblique asymptote, it is actually an asymptote that has a slope other than 0. Okay? So I'll give you an example of this. And that slope could actually change throughout the asymptote. So it could be your oblique asymptote could be non-linear, could be a quadratic, could be a quartic, whatever. So let's just do one that's, if I do that 3x squared and divide that by x, that's kind of boring. Let's do 3x to the third plus 2x squared plus 0.3x. And we'll divide that thing by, let's go x plus 2 plus 2, and then x minus 1. Let's see here. Let's actually get rid of. What we have here is no longer a horizontal asymptote. And this graph is kind of ugly here, but you see it is kind of cubic in nature at this region, right? Okay, in this middle region. But now my asymptote is no longer horizontal. My asymptote is going to be, and we have to do the long division to actually find out what the asymptote's equation is. But if I look at that line right there, okay, does that line in the long run kind of look like an asymptote for this function? Mm-hmm. Okay. So we'll be able to go through the algebra and find that equation of that asymptote. Okay. And the way we do that is we use the long division technique that we've learned in 3.1 and 3.2. Okay. So chapter 3 or section 3.6 and section 3.7 ultimately are a culmination of everything we've done so far this year. We do a lot of domain stuff, okay? Looking at denominators and seeing where the denominator cannot be 0, where you cannot divide by 0. So that was like what, chapter 1, chapter 2 a little bit. We're going to do the graphical stuff that we've been working on throughout the entire course, finding x-intercepts, y-intercepts, that kind of stuff. but there's, in regards to chapter 3, the things we've done in chapter 3, there's going to be quite a bit of factoring. Okay? So, everything we've done so far this year, if you felt comfortable with everything we've done so far this year, you should be okay on this stuff. The only thing that becomes problematic is there's like 12 steps to every one of these. So chances are somebody's going to probably do 11 of the 12 steps and forget the 12th one, right? Or you might do, not every one of them deals with 12 steps. You might come across one that only forces you to do 4 steps, and the next one might force you to do 4 steps, and the next one might do 4 steps, and then the next one does 7 steps, and you forget that there's extra steps because you've gotten ingrained in the process of doing 4 steps, 4 steps, 4 steps, and then you try just to do the same thing on the next one. Okay. So as you work on these, I'm going to give you some rules. The rules show up under 3.6. Those are kind of going to be your best friend as you go through some of these. But and we'll do an example here before we leave, but as you work through your homework throughout the next couple days, and right now I've pushed it back to at least Wednesday, so start working on it now. But you want to kind of deal with this stuff here. We're going to find the numerator and denominator, and we're going to factor them. Okay, so I'm going to do an example here, and we'll jump back and forth between that slide and this example. Okay, it says 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. Okay, when we deal with these functions, and we want to, the whole goal of this is to develop a comprehensive graph to understand what our graph or function is doing for us in the xy plane. Okay. In order to do that accurately, it's a good idea to actually have both formats in front of you. And what I mean by both formats is have the expanded version, 3x squared minus 2x minus 1, and 2x squared plus 3x minus 2. Have that in front of you, but also have the factored form in front of you. Okay? So here's where some people kind of run into an issue, is because we haven't really realized the necessity of factoring. We haven't spent a whole lot of time, maybe on our own, developing our skills for factoring, but now it becomes a preliminary step. Okay? And this is something that you'll see in a calculus class where maybe I get this function, I want to integrate this function, or I want to differentiate this function, and I've got to factor things first. I've got to know what this graph looks like first before I can do those things. So we work through and we try to factor this. Okay? Now, in that bottom one, they already factored for us, so I'm going to because we're running out of time, kind of cheat. But that gives me 2x minus 1, and was it x plus 2? Now, the only way, the reason they did it that way, okay, or how they found that, is that they just used the a times c method. 2 times negative 2 gave you negative 4. Now find two numbers that multiply together to give you negative 4, and have to give me 3, and factor it. Okay? We'll factor the top one the same way. Okay? So 3x squared minus 2x minus 1. I'm going to kind of do that work down here. 3 times negative 1 gives me negative 3. So now the two numbers that multiply together give me negative 3, but have to give me a negative 2 are 3 and negative 1, right? So now the a times c method says that becomes 3x squared plus 3x. I got these backwards on. Minus 3 plus 1. And then minus 1. Okay? So the a times c method really is just giving you a technique to rewrite that negative 2x, right? As a sum. We'll group those. 3x comes out of the first two, gives me x minus 1. And then 1 comes out of the back two, give me x minus 1. So now that factors to 3x plus 1 and x minus 1. Is that doable? Alright. So what's really nice about that is that those two formats tell me pretty much everything I need to know. Alright, we just have to do small individual equations, one-step equations. Okay? First thing I want to do is find vertical asymptotes, because I think that's the easiest thing to do. Vertical asymptotes are when the denominator is equal to 0, right? Okay, it's where you cannot divide by 0. So what is that going to provide me? 2x minus 1 is going to provide me a 0 where? 1/2. So a vertical asymptote at x equals 1/2. Okay, where is that one going to provide me? Negative 2. So now I've got a visual in my mind of two asymptotes at 1/2 and negative 2, and they're vertical and I can't cross those. Okay? The next thing I'm going to do is I'm going to find horizontal asymptotes. Okay? Now in this format, horizontal asymptotes are kind of hard to find because I don't have, it's kind of hard to see here that this is a 3x squared as my leading degree, right? Or leading term. 2x squared is my leading term here. Okay? Looking at this, format, it's a little bit easier to see what my leading terms are, right? The degrees are the same. Okay, so if you remember n equals m, okay, then you divide your leading terms, right? Your leading coefficients. So in this case, I have a horizontal asymptote at y equals what? 3/2. Okay, so those are some nice things to have for our function. Now, in your homework, a lot of your questions were asking you stuff like that, kind of, just for this question, give me asymptotes, okay? But we'll also want other things. What if I wanted the y-intercept? What is x on all y-intercepts? 0. So does that go to 0? 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 So those things wipe away, and what am I left with? 1/2. So y-intercept, best looked at that form right there that is provided in the PowerPoint. Our y-intercept, x is 0, y is 1/2. Okay? X-intercepts. X-intercepts are when what is equal to 0? Your y value, right? Okay? X-intercepts is when y is 0. So this is the y, r of x is your y, right? So can I say 0 is equal to 3x plus 1 times x minus 1 over 2x minus 1, x plus 2? When you have a fraction inside an equation, what do you always try to do when you're trying to solve for a variable? You always try to multiply by what first? Common denominator, right? Get that thing to go away. So when I multiply both sides by this denominator, right? Well, when you multiply 0 by that denominator, what do you get? 0. You get 0. And this will go away, right? On that side, when you multiply that side by that denominator. So you should get your numerator equal to 0, right? So when you want to find x-intercepts, and this always works, this is the shortcut. When you want to find x-intercepts, it's just when your numerator is equal to 0. Because you always go through that process of multiplying both sides by your denominator, while multiplying 0 by my denominator is always going to give me just 0 equals my numerator. Okay? So set that equal to 0. So the benefit of having it factored already, x equals negative 1/3, and x equals 1 for my x-intercepts. So now you got a vertical asymptote, you got an x-intercept, you got a y-intercept, you got a horizontal asymptote. You got a lot of stuff for your graph, right? Okay? And we'll start plotting those things, plotting those points, plotting those asymptotes, and then understand how a curve behaves around an asymptote, and it will give us a pretty good, it gives us this graph right here, okay? Which is pretty easy to find after we've got all this stuff, okay? Individually, like I said, each of these things I think is pretty easy, right? Factoring just this numerator wasn't too bad. Factoring just that denominator is not too bad. Finding these zeros at the bottom is not too bad. Finding the zeros in the numerator is not too bad. But when you have to do all that stuff together, people make mistakes, okay? And there's going to actually be some other additional things that we have to worry about, and we'll kind of concentrate on those tomorrow. Those are holes of our function.